Thank you. Thanks again for joining Scalar. I hope everybody will finish their break soon as well. So I would like to share my recent work, an experiment that is ongoing into how it might feel to actually write an application using the direct style in Scala. So there will be a short demo in the middle. First, we will talk a bit about an introduction what a software stack in general is. But then I will leave you with some open questions as to what we might work on next and what we might research next, and hopefully maybe you can help answer those questions. Okay. So first. Let's consider what a software stack is in the first place. So if you try Googling it, we can read that a software stack refers to the set of components that work together to support the execution of the application. So on the lower level, you can think of it as the set of like helper tools, utilities, some common methods that you might use when writing your application. On a higher level, this might be components that are already there, which you can reuse and from which you can combine your application. And of course, all of these should somehow adhere to the same programming style, right? They should support you in your chosen programming style. So it's not a very strict definition, but I think we all have kind of an intuition of what a software stack actually is. And we have a couple of software stacks in Scala, and they all work pretty well. So for example, we have the cause-effect stack, right? Where we program using the tagless final style very often. We use the IO monad. And also to support us in this purely functional programming style, cause-effect provides us with an asynchronous runtime where we have fibers for concurrency and stuff like that. On the other hand, we also have Zio, which takes a slightly different approach, also a purely functional stack. It uses a fused effect monad. And also provides us with an asynchronous runtime, which is very similar to cause-effect. We also have the Pecco and Future stack, where if we want to do like distributed cluster computing, or if we want to do event sourcing, it's a great basis for such use cases. So there we've got that's based on actors and on reactive streams, which we encounter quite often. So these stacks are great, and if you want to start a new application in Scala, these are all good choices. So why would we even consider a new one? That's always a good question to ask before doing any work. So before actually answering this, I would like to back up a bit and think a bit about why did we end up with using IOs, with using the IO monad in the first place, right? And as far as I remember things, I think some of you might have different opinions, but as far as I remember things, we used to do a synchronous thread per request model a long time ago, like 10, 15 years ago. But this very soon hit some limitations, right? Because we were limited by the thread pool that we were using. And threads are an expensive resource. They are expensive to create. They take a lot of memory. They are expensive to switch between. So we started pooling them and so on. But we have hit performance and throughput problems. So people came up with the idea of using asynchronous I/O. And to use asynchronous I/O, they had to do callbacks. So we ended up in callback hell. So then people improved upon that. We ended up with futures. And then the futures met with purely functional programming, as it is known in Haskell. And in a combination of these two, we got the I/O monads that are there. However, now, we have Project Loom and virtual threads, which kind of changed the landscape, and they change the way we might do programming on the JVM, because that's the scope so far. So what Loom did is it introduced the asynchronous runtime that we used to have in cause-effect and Zio right into the JVM, and it made it possible to program using direct style, using synchronous code, having the benefits of the asynchronous runtime right in there. So in a way, the original reason why we used I/O went away, right? Because we can do the imperative direct style programming and still get the benefits of the asynchronous I/O. So we can get the throughput, the performance, the concurrency that we had because of using futures, I/Os, and so on. Of course, there's a lot of other reasons why you might use I/O, but it is not immediately clear that actually the good sides, the other benefits of using I/O benefits outweigh the costs that come with using a monadic programming style. So in a way, the world has moved forward, and Scala has a lot to offer. I think it is the best and probably only commercially used language that combines functional and object-oriented programming. So we still have a lot to offer to the programming world. But in some use cases, probably in the simpler services and the smaller services, to stay relevant in the new world where we have Project Loom, where we see synchronous programming making a comeback, we need something to stay relevant. So going forward, we will think about how we can really support execution of applications written in direct style when using Scala. So we will go through some example code, so you can see a couple of components and a very simple application written in direct style, so you can maybe get a feeling of how it works. Our application will be a very simple web application, so we will have a single endpoint, and of course it will have something to do with AI. So as an input, we will ask questions to our application, and our first AI applications will then it will try to answer your question as fast as possible. So it will do two things concurrently. It will look up an answer to the question in the cache. So if the question was asked previously, we will just return the old answer. And at the same time, we will query an LLM to actually generate an answer for us. And then we return the answer to the user. And if we have generated a new answer, we also write the answer to the cache in the background. So a simple application, but a couple of things will be happening there so that we can demonstrate things. Okay, so let's start with the web layer. Of course, we are going to use Tapir because that's our own library, so what else? First of all, we will describe the endpoint which we will invoke. So far, nothing special about direct style. It's just a data structure describing the endpoint. The path that we are going to use is fast/AI. As an input, we are going to take a single query parameter, and we are going to map it to the question data class. Nothing special about the question class. It's just a wrapper so that we know we can distinguish questions from answers. And we return the answer as a string body. So that's the description of our endpoint. But now we want to implement the server logic using direct style. So what we will do over here is we will take our endpoint and we will couple it with the server logic. So as the effect, we will use identity. Identity is kind of a no effect. It's just a no-op wrapper for any type. So we don't represent effects in any special way. We will just do synchronous programming. Okay, so what we have to do inside in this server logic, so we have the question over here, right? And now we want to answer, so we have to raise two computations. One of them will query the cache, and the other one will query the LLM. So we want to do a raise. And this raise either method, so the first library that we have seen here that helps us write direct style code is Tapir using the identity or the synchronous server logic. The second is Ox. Ox is a library which helps you write concurrent programs in Scala using direct style. So what the raise either method does is it takes two code blocks and it executes them in parallel. And whichever finishes first successfully is taken as the winner, and the other is discarded. So there's a couple of variants of these race methods. So sometimes success means that it produces any kind of value. So here we are not really interested in any kind of value. We are interested in successful values, right? So our cache lookup might end up saying there's nothing in the cache. So that is a successful result in a way of lookup in the cache, but it's not what we are interested in, right? We are only interested in the case when things are in the cache. So the basic race variant uses exceptions. Here we have a variant which uses eithers. So that's like kind of a different error mode. There's a couple of error modes that are supported by Ox. And these error modes specify what is considered a success and what is considered failure. So it's, of course, in addition to exceptions. So the first branch of the racing will be looking things up in the cache. So we are using Redis as the caching solution, and we are using a Redis client, which is a Java client, which will wrap with Scala. So a very simple method, right? We are using the get over here. So the get is blocking, but that's fine because we are running all of that on virtual threads. So the race either will actually spawn 2 virtual threads to perform the race. So the get here is blocking. We are blocking virtual threads. So that's completely fine. Wrapping it in an option to decide if the value is in the cache or not. And in the end, we have to convert the option to an either to satisfy the contract of race either. And in the second branch, we will actually query OpenAI because every AI startup doing LLM stuff in the end calls OpenAI. So we are doing the same. So to query OpenAI, we can go down here. So what we are doing, once again, we are creating a description of a request that we are going to send to OpenAI. So let's see how this looks like. So the request, so that's the method which creates a description of the request. It's an HTTP client description. Again, here we are just creating a data structure, so nothing which touches upon an effect. It just describes the shape of our request. We are going to OpenAI, to the chat completions endpoint, and as the request, we are sending a completion request. It's going to be serialized as JSON. And here's the definition. You can see that it derives a read writer which comes from Yupical. So this will be automatically derived for us the codec. And as the response, we get the completion response, and we get the first completion out there. So that's the description, and we still have to send it. So to do that, we use a synchronous backend. So once again, we use the blocking.send method, where we simply block the current virtual thread on which we are running to send the HTTP request and wait for the response. And in the end, we convert responses into a none or some. And if you go up here, you can see that we then convert the option to an either to satisfy the race either. I will talk about updating the cache a bit later. We also do a thread.sleep here, so we are optimistic that the question is in the cache. So just in case, we take our chances and delay querying OpenAI and using our precious credits for a bit. In direct style, if you want to sequence 2 computations, you just write them one after the other, right? That's a blocking operation, and that is also a blocking operation. Okay, so what we also do here is we want to update the cache with the result in the background. We don't want to block the clients before with the cache update. So what we do is, as a parameter here, you can see that there's a sink where we can send requests to update the cache. So async, it's an interface implemented by a channel. That's also a data structure that's provided by Ox. It's a concurrent data structure, a bit like a queue, but some additional capabilities. So what we do, we send an update cache task to the sink. We also, but we don't want this really to block in case the queue of updates is full. So we select, so this select is something that you might note from Go. It selects one of the clauses to complete. So if it can send because there's still space in the buffer, we do. If it doesn't, it just returns a default of a unit, and the cache isn't updated. Okay, so that is the endpoint. Now let's look at the application itself. So first of all, we have the endpoint description, we have the endpoint logic, but we still have to expose things to the outside world. So the first thing that we need to do is we need to actually allocate a couple of resources. For example, we have to set up the Redis client. We have a setup method for that over here. You can see that we simply connect to a locally running Redis. We make Redis virtual thread aware by setting a proper executor, and that's about it. But we also need to, because it's a resource, we need to close it when our application finishes. So one way to do that would be to use try finally and to wrap this whole thing in a try finally block. But that isn't perfect because the closing logic is very far away from the allocation logic. So this kind of spreads across your code. So what we can do instead is we can use a supervised scope. Again, something that comes from the Ox library. So supervised scopes, they define structural boundaries within which you can fork concurrently running computations, and they are the basic building block for structured concurrency. So within a supervised block, you can fork new computations, and they are guaranteed to finish or to be interrupted before this supervised block finishes. So the lifetime of any concurrent computation that you start is defined by the structure of your code. So this supervised block finishes right over here. So when control exits this supervised block, we are certain that any background computation that we have started are interrupted or have finished successfully. But we can also attach resources to such scopes. So we can say that before the scope finishes, make sure to shut down this Redis client. So that's what we are using here. We are wrapping it in using scope. We are doing the same with our HTTP STTP backend. So that's for allocating resources. And in the end, we need to actually bind our HTTP server. So here we invoke the method that we have talked about before, which actually creates the server endpoint. And we pass it to our netty server over here. So that's the list of endpoints that we want to expose, a single endpoint. We pass it to our netty server, and we start it. So starting an HTTP server using netty and Tapir integration is quite easy. We just create a netty server, we add endpoints, and we call .start. And that's about it. We also generate some documentation endpoints so that we can actually easily invoke the endpoint. So let's try running this and see if this works. If this works, okay. We get the documentation. Try it out. We can ask a question. What is the best Scala conference? Execute. And let's see what OpenAI says. The best Scala conference in Europe is Scalar, of course. That's very easy. We can ask what's the best Scala conference in the world. We can execute. Oh, okay. Once again, Scalar. So we can see that the bias problem in AI is real because it seems to always answer Scalar. But you can test with another question like who is Albert Einstein? Maybe it's Scalar as well, or maybe not. And actually, it provided a reasonable answer. So we are indeed querying OpenAI. We can execute this once again, and this time it's immediate because we got our answer from the cache. So there's one more component which we need to discuss over here, which is updating the cache. So we have seen how we can enqueue things how we can enqueue tasks so that the cache is updated. So we have this sink over here where we can enqueue update cache tasks. But we also need some kind of consumer that will actually update the cache. So that's what is done over here. So over here, we have our method run update cache, and this method requires to be run within a concurrency scope. So here we have the using Ox. Ox is a capability which specifies that you can actually fork concurrently running computations. And if you see a using Ox, this means that we must be run within a concurrency scope, right? And we are, because the supervised block over here provides using context functions that are available in Scala 3, it provides the Ox capability to the body over here. So we've got the run update cache, and what it does is it creates the channel that I've been talking about. So that's our queue of cache update requests, and we are going to return that to the client, and then it's going to be passed over to the endpoint. But it also has a side effect, and it has a side effect of starting a concurrently running computation, so a fork. So this will start a new virtual thread, which will do some computations, and what it will do, it will run forever. It will run forever. It will receive a single task from our update cache tasks queue. And what we will do is we will update the bucket. We will update the bucket with the answer again in a blocking way. Actually, there's a problem here. We should use non-fatal. To respect interruptions properly, because if the scope is finished, so if the supervisor decides that the scope should be finished, it will actually interrupt any forks that are running still. And if the interrupt happened over here, it would be eaten, and that would be a bad thing. So we never should catch all exceptions. We should just catch non-fatal exceptions. So, but this whole pattern, if it resembles an actor, that's perfectly correct, because it is kind of an actor, right? We have a message queue, which we return over here. So that's the way to communicate with the actor. That's the type of messages that the actor handles. And that is the actor body, where we read a single message and read a single message and process it in some way. And this is always, run in a single in a single thread. Okay, so I guess that's about it for the one more thing that I wanted to show is how easily you can integrate things like telemetry, which is sometimes tricky with functional effect systems. So here what we can do is, if we go to our Netty server, we can see that we add a request interceptor over here. And this request interceptor, what it does is it decorates our request with some tracing. So what we just need to do is we need to use a fork local. So that's like a thread local, but specialized for virtual threads. And we can set the current span and the current trace in a fork local, and so the F over here would actually proceed with processing the request. So with this simple interceptor over here, we can report traces, and if we go to something like Jaeger to visualize our traces, we can see that we have a couple of them over here. So this one, for example, went to OpenAI, right? Because it completed the cache lookup very fast, but then we had to do the HTTP call to OpenAI, and this one was very fast. It interrupted the OpenAI call because the race was won by Redis. So because we all live in a structured, in a direct world, what we just need to do is we can decorate things in a very usual way. Okay, so the component that we have seen, of course, as the foundation of our stack is Scala, is our programming language. For error handling, we are using exceptions. Mostly the exceptions that we have seen here will be used for things like bugs, probably. And for any application errors that we want to represent as values, we are using eithers. For structured concurrency, we are using either the high-level combinators like raise either, or we can use the lower-level supervised and forks. For resource management, we have the option of try, final, and scopes. So all of these have, they are not all perfect, but with some discipline, they work just fine. And of course, a very important aspect is the ecosystem, right? So that's like the libraries that we have seen here are just the basis, but we also need a whole of other tools to make in our daily work. So a lot of libraries already support direct style, and STTP and Tapir are just a start. But for those that don't, we can quite easily bridge, for example, with any library that uses futures, because we can simply block on the future and await the future, and that is completely fine in a virtual thread world. And we can also wrap Java libraries, which are often direct style aware. So this is JVM only, so that's kind of a downside. However, there is some work to make this work on native, and I think we will see a bit of that tomorrow in Gears. There's something that we gain and lose comparing to I/O, so it's not an obvious win, but it's certainly something to look at. And before we conclude, we still have 4 minutes, that's good. So I think that going further, a question that we would like to answer, or which I would like to answer, is asking what kind of properties should our ideal method signature guarantee, right? So now if we look at this method signature over here, we can see, no, it's a query LLM, that's fine, it takes a question, and it can return either an error or an answer, right? Because very often things can fail. And here we represent only application errors, right? So this error might include things like that there's not enough tokens left and that we must buy more. But probably if there's an I/O exception, like a broken connection or something like that, we will get an exception. And that's not visible in the signature. So that's probably not ideal, right? So maybe instead, we would want something like this, right? Where we can see that we can get either an LLM error or an I/O exception, here represented using a union type, or our proper answer. So maybe that's the ideal method signature that we would want. Or there's yet another possibility. Maybe we would want to use a capability, right? We had the capability of forking concurrently running computations, so maybe we can have an I/O capability which would say, in a more coarse-grained way, that I/O exceptions might happen when executing this function. But then, if we use such capabilities, the question comes, should this capability be eliminatable, right? So if all errors are handled by some caller, should it still require the I/O capability or not? So here, for example, we have a method which calls our query LLM method, and it catches all non-fatal exceptions. So, in itself, the answer method will never really throw an exception, right? So, should it have the I/O capability in its signature or not? So, from a timing perspective, of course, it might take an arbitrary amount of time, but from the error perspective, it won't really throw any errors. So there's a couple of these capabilities that we might come up with, right? We have seen the Ox capability, the capability of forking concurrently running computations. We might imagine having a state capability, the capability of actually modifying a global state, of using I/O, or maybe of an async capability, which is a capability to suspend, which I think also is a feature of Gears. There's, of course, the problem of how do we actually verify these capabilities, right? So maybe, in the case of I/O, for example, there can be a compiler plugin which inspects the bytecode and says, you are using the Java I/O over here, so this would need the I/O capability, for example. So it might be not trivial, but it might also be possible. So if you would have any ideas of what the ideal method signature should be like, you can either find and talk to me over here, or you can join us on the community forum if you would like. We would be very interested in your feedback. So before I conclude, I also would like to invite you to our company stand, learn a bit more about the open source we do, about the kind of services that we offer. And there's a couple more presentations during Scalar that touch on similar themes. So there's, first of all, structured concurrency in direct style with gears by Nguyen tomorrow. There's a presentation by Jacek, which dives a bit deeper into channels and retries. And there's a presentation by Wojtek on how to do similar things, but on Scala native. This presentation is available on GitHub if you'd like to play with the code or inspect it in a bit more detail. Ox is an open source project under Apache 2. It's released on Maven, so you can play with it as well. And I think that's all. Thank you. 5 seconds.
4 seconds left. Wow. Thank you.